Hello everyone, I am G. Nirnay Rao from Department of ECE. Today I will present the Cayley-Hamilton theorem, a concept in linear algebra particularly for two-dimensional systems. Linear algebra is the backbone of many fields including engineering, physics, engineering and computer science. It helps us understand system of linear equations, transformations and how data behaves in multi-dimensional spaces. Matrices, which are array of numbers arranged in rows and columns, are central to this understanding. A square matrix where the number of rows and the number of columns can represent a system of linear equations or a linear transformation. One of the most important properties of a matrix is its eigenvalues and eigenvectors, which reveal how the matrix transforms vectors. The Cayley-Hamilton theorem, one of the most fundamental principles in linear algebra, as we all know. This theorem is not merely theoretical, it provides powerful computational shortcuts for matrix operations. Mathematicians Arthur Cayley and William Rowan Hamilton asked a simple yet profound question. Can a matrix satisfy its own characteristic equations? Yes, the Cayley-Hamilton theorem answers this beautifully. Every square matrix does indeed satisfy its own characteristic equation. This is not just a theoretical curiosity. It has important practical applications in simplifying matrix computations, solving differential equations, analyzing control systems, and many more. In the next few minutes, we will explore how this theorem works for 2 by 2 matrices, see its formula, understand and characteristic polynomial, and finally look at its applications. Statement of the theorem for 2 by 2 matrices. Now let us state the Cayley-Hamilton theorem formally. Every square matrix satisfies its own characteristic equation. We can say it in simpler words like if you find the characteristic equation of a matrix and replace the variable with the matrix itself, the result is the zero matrix. We will get on to the example later. For 2 by 2 matrix, the Cayley-Hamilton equation is expressed as a square minus trace of a plus det a into I equal to 0. Here A is the matrix itself, trace A is the trace of the matrix, which is sum of diagonal elements. Det A is determinant and I is the identity matrix. In simple equation, we can represent it like this. This is simple but yet very powerful because it allows us to represent higher powers of a matrix in terms of lower powers, saving time and computation. Characteristic polynomial and matrix substitution. For a 2 by 2 matrix, we can understand and explain it. We first need the characteristic polynomial. For a 2 by 2 matrix, the characteristic equation comes from a minus lambda I equal to 0. For suppose, let us consider a 2 by 2 matrix A equal to A, B, C, D. Expanding the determinant of this matrix, we will get A minus lambda into D minus lambda minus BC equal to 0. Simplifying, we get the characteristic polynomial lambda square minus A plus D lambda plus AD minus BC. Here A plus D is trace and AD minus BC is the determinant. According to the Cayley-Hamilton theorem, If we replace lambda with the matrix A, the polynomial becomes a square minus trace of A plus det of A into y equal to 0. The we can also verify it. The resulting matrix polynomial equals to 0 matrix. This verification can be done through direct algebraic computation, demonstrating that the theorem holds universally for all 2 by 2 matrices. Multiplying A by itself and substituting confirms that it equals to 0 matrix. This illustrates the theorem perfectly. And here are some worked out examples for this. First, we have to calculate the trace and determinant, compute for A square, form characteristic equation, and verify the theorem from this. Here we can see in this equation, this question, that verification is correct, so this can be done. And now come on to the proof outline for 2D systems. The proof of the Cayley-Hamilton theorem for 2 by 2 matrices can be established through several elegant approaches like algebraic expansion method, adjugate matrix approach, and Cayley-Munhagen construction. If we come back to the algebraic expansion method, we can directly compute by the equation by performing matrix multiplication and addition. Expand each element and verify that all entries sum to 0. Adjugate matrix approach using the relationship mentioned here. Now coming on to the applications in 2D linear systems. The Cayley-Hamilton theorem is not only elegant, but it is very useful for computing higher powers of a matrix, that is, matrix power reduction. The theorem enables us to express higher powers A power n as linear combination of A and I, avoiding computational expensive repeated multiplications. For example, for calculating A power 4, A power 5, etc. Control systems engineering. It is used to calculate the state transition matrices in state space analysis. Differential and differential equations. In solving linear systems of differential equations or discrete time difference equations, the theorem simplifies calculations in control theory and signal processing applications as mentioned above, like calculating exponential like e power 80, which are important in system modeling. Simplification of calculation helps us in reducing complex matrix operations and by using the most simplest terms of the matrix, that are trace and determinant. Matrix inversion. For invertible 2 by 2 matrices, the characteristic polynomial coefficients provide a direct formula for computing A inverse without explicit division and generations. Thus, this theorem is widely applied in both theoretical and practical problems. Visualizing the impact before and after. In the traditional approach, computing A power n requires n-1 sequential matrix multiplications. But after the Cayley-Hamilton method, the theorem reduces A power n to a linear combination of A and I, which are the simplest terms of matrices. To summarize this, the Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic equation. For 2 by 2 matrix, matrices, this is written as A square minus trace of A plus det of A into I. His simpler matrix computations helps find higher powers of matrices and is extensively used in engineering applications. Conceptually, it shows that every matrix knows its own algebraic identity defined by its trace and determinant. In conclusion, the Cayley-Hamilton theorem is an example of how elegance and utility combine in mathematics. It is a very powerful mathematical tool especially in engineering. It also bridges theory and practice, connects matrix algebra fundamentals with polynomial theory, eigenvalues, and eigenvectors, unifying multiple areas of linear algebra into one coherent framework. Foundation also makes foundation for higher dimensions. Understanding the 2D case provides the conceptual foundation for extending into 3D, 4D, or generally n-dimensional systems in advanced engineering coursework. Thank you very much for listening. I hope this presentation gives you a clear understanding of the Cayley-Hamilton theorem for 2D systems or above.